All right, students, today we are talking about chapter 5 in the textbook, which is the normal distribution chapter. So this is one of the more difficult chapters, one of the weirder chapters of the textbook. So once you get a little bit of exposure to this, it should be, at least some of the other chapters should be a little bit easier in my opinion. So this is usually the first time anybody's ever seen something like the normal distribution and the appendix. So like I said, this will be a rough probably introduction, but the next couple of chapters should be a little bit easier after we go over this chapter. All right, so today we're going to be talking about the normal distribution. And what is a normal distribution? If you all remember from, I think, chapter 3, the measures of central tendency, we're talking about different types of distributions that you might see if you have interval ratio level data. Okay, so you might see symmetrical, you might see positively or negatively skewed distributions. And of course, this applies to interval ratio level data. If you have nominal and or ordinal level data, typically you're not going to see a distribution that is normal. And if you do, it's just a coincidence. And you don't really see normal distribution because with nominal and ordinal level data, because with nominal and ordinal level data, you don't create histograms, so you would never really see like a bell-shaped unimodal distribution. So like I said, when we're talking about a normal distribution, we're talking about means, we're talking about standard deviation. This applies to interval ratio level data. Okay. So let's talk about how you know if you have a normal distribution, some properties of a normal distribution. So a normal distribution or a normal curve looks like a bell-shaped frequency. Okay, so the normal distribution is perfectly symmetrical, meaning if you fold a normal distribution in half, the two equal halves will be mirror images of one another. So if you all remember what we were talking about in chapter 3 with a symmetrical distribution that I drew up there is a normal distribution. So a normal distribution looks like a bell-shaped frequency. And the reason why they say it is bell-shaped is because if you take like, let's just say that there's a rope here, think about like moving the rope back and forth, you're ringing a bell, so it looks like a bell. Obviously, the other part is if you cut it in half, left side and right side are essentially mirror images of one another. So this is what a normal distribution looks like. Bell-shaped, unimodal, symmetrical distribution. And like I said, there's also positively skewed distributions and then negatively skewed. Negatively skewed distribution, but today we're not going to be talking about positive or negatively skewed distributions. We're talking about symmetrical, unimodal, what we refer to as normal distributions. All right, so let's talk about some other properties of a normal distribution, how you know that you have a normal distribution. So one, you could just examine it visually, and if it looks like a bell, if they look like mirror images of one another, then you generally know that you have a normal distribution. The other way is to determine it mathematically, and the way you determine it mathematically is by calculating the three measures of central tendency: mean, median, and mode. Okay, and if the mean, median, and mode are all the same number or are relatively close, you know you have a normal distribution. If you remember a couple chapters back, if the mean is substantially higher than the median, then what you have is a positively skewed distribution because you have a few extreme outliers on the high side, pulling the mean higher than it should be. And if you have the mean is substantially lower than the median, then you have a few extreme outliers on the low side, pulling the mean lower than it should be, okay? So that's one way you calculate the three measures of central tendency. They're all relatively close. You know you have a normal distribution. Now, one thing that's important when we talk about the normal distribution is to understand it's a theoretical ideal. And what we mean by that is that very basically no real world distribution ever perfectly matches this model. So sometimes I show students normal distributions and then they say, oh, well, it's not perfectly symmetrical, so it's not normal. Well, no real world data is ever going to be perfectly symmetrical. No real world data is ever going to perfectly match this. However, a lot of real world distributions closely resemble the normal distribution, okay? And because a lot of real world distributions closely resemble the normal distribution, we can learn a lot about real world distributions based upon what we know about this theoretical normal distribution. So, you know, if you see a distribution that looks kind of normal, but you're like, well, it's not perfect, you're never going to see a perfectly, you know, symmetrical, perfect normal distribution in the real world, okay? So taking a look at this, let's just say that these are the final grades in my stats class for 45 students. I know it says 44 there, a mistake. Textbook created this, not me. But so there's 45 people, okay? And these are the final grades. Now, like I said, we're looking at a frequency distribution. So these are actually the scores, 50, 60, 70, 80, 90. And this is the frequency here. So these are the frequencies for each score. So 5 people got 50, so 5 people got Fs. 10 people got 60, so 10 people got Ds. 15 people got 70, so 15 people got Cs. 10 people got As, and 5 people got 90s, okay? So these are the scores. And these are the percentages here. So looking at this, does this distribution look normal? And then there's a couple ways to examine it. And the first way to examine it is to examine it visually, okay? Well, if you look at it visually, let's just say that you were to draw a line around this distribution. So you start up here, you go around, looks like a bell shape to me, okay? If you were to cut it in half, the left side and the right side are, for the most part, mirror images of one another. So looking at this, examining it visually, certainly appears that we have a normal distribution here, okay? Now, the other thing that we can do is we can calculate it mathematically to determine whether or not we have a normal distribution. So we'd have to calculate the mean, the median, and mode. Now, let's go ahead and knock out the mode because that's going to be the easiest one to do. How do you go about calculating the mode? It's just the category with the largest frequency. Okay, so since we know that 15 people got 70, we know that the mode is 70, so we can just go ahead and write mode is equal to 70 here. Now, what we'd have to do to calculate the median is to create a cumulative percentage distribution, okay? So hopefully you all remember what a cumulative percentage distribution is from chapter 3. What you do is you add the percentage from the first category to the next categories and so on until you get 100% of the distribution. So we know that the percentage in the first category is 11%, right? So let's just say you have a C percentage over here. I guess I'll kind of try to draw it. C, and then percentage. I'm drawing this with a mouse, so you know, it looks pretty bad. So this is cumulative percentage. And then for the first category, we know that the cumulative percentage is still just 11. So I'm going to draw the cumulative percentage up here. So cumulative percentage here. First category is 11%, okay? Then what we do is we add that to the next category. We know the next category is 22%, okay? So since the next category is 22%, what I'm gonna do there is I'm going to add 11 to the 22, okay? And then 11 plus 22 gives me 33, okay? Now that we have that 33, we're gonna add that 33 to the next percentage, which is again 33, so it gives us 66%. Add that to the next percentage, which is 22, which gives us 88. Then add that to the last percentage, which is 11, which is approximately 100%, so 99%, small rounding errors. And we have a cumulative percentage. So the percentage, if you all remember how to find the median in a frequency distribution, what you do is you're looking for 50% mark. Now, you don't see 50% here, you see 33 and 66, you know it's in between these two categories. And then if you remember from chapter 3, we go down. So it's gonna correspond to the 66%. Now, if you look back to that frequency distribution, if we have 11 here, 22 here, 11 here, 33 here, 66 here, 88 here, 99 here, then we know it corresponds to that 66. The median is 70. So we know our median is 70. And then the last thing you would have to do is you would go about calculating the mean. Now, how do you go about calculating the mean and the frequency distribution? Hopefully you all remember this. What you do is you multiply the frequency by the raw score. So what you would do here is you would do 50 times 5, and then to give that score of 50 its proper weight, 60 times 10 to give that score its proper weight, and then so on and so forth, add them up and then divide by the total number of cases. We have 45 students, and the way I know we have 45 students, we have 5, 15, 30, 40, 45. Okay, so I'm just gonna go ahead and do that. 50 times 5 gives me 250. And then we go 60 times 10 gives me 600. We go 70 times 15 gives me 1050. 80 times 10 gives me 800. And then 90 times 5 gives me 450. So that's what you calculate. Well, that's how you start calculating the mean with the frequency distribution. Now what you need to do is you need to add all these scores up. So you do 250 plus 600 plus 1050 plus 800, then plus 450. You're going to get 3,150 when you add these numbers up. So now you have the top part of the equation done. So the top part is 3,150. Then you divide that by the n, which we know is 45. So 3,150 divided by 45 gives us 70. Gives us a mean which is equal to 70. So our mean is also 70. So since we know that our mean, median, and mode are all 70, we know that we have a normal distribution because we examined it visually. It looks normal. We calculate the measure of central tendency. Again, it looks normal. So we have, well, they're all measures of central tendency are essentially the same. So we know we have a normal distribution on our hand. Okay. So again, this is essentially what the normal distribution is supposed to look like, normal curve. This is just a better drawing than what I can do by hand. Okay, so the shape of the distribution. Now, as we stated already, a normal distribution tends to have the majority of observations at the middle part of the distribution. And as you get further and further away from the middle, from the center, which is where the three measures of central tendency coincide, you're starting to see less and less observations in the distribution. Now, what you're looking at right here is a relatively good example of how, again, a distribution might not be perfectly normal, but it's still a normal distribution. So if I were to draw a line around this, as you can see this line, it's a bell-shaped frequency, bell-shaped distribution. As you can see as well, you do have more, I guess you could kind of see, it seems like there's more observations on the right side than on the left side, so it's not a perfect mirror of each other. However, it's still close enough to be a normal distribution, so we know here that we have a normal distribution. Okay, now we're going to learn what the usefulness or what the value of the standard deviation is, because last chapter, in chapter 4, we learned how to calculate the variance and we learned how to calculate the standard deviation. And I kind of loosely talked about what it does. I mean, I said that it gives you the general give or take around the mean, but it also provides more information than that. Okay, so when we have a distribution that is either normal or approximately normal, and we know both the mean and we know the standard deviation, okay, so we need to have those pieces of information. We need to make sure our distribution is normal. We need our mean and we need our standard deviation. Then we can determine the percentage of cases that fall between any score and the mean, or we can determine the percentage of cases that fall beyond that score. Okay. So since we know that our mean here is 70, and the way we go about doing that is by calculating a z-score, okay? We know our mean is 70. In order to calculate a z-score, we also need our standard deviation, okay? So before we start talking about z-scores, let's go ahead and calculate the standard deviation there. So if y'all remember, maybe you don't, but if you don't, I'm gonna quickly review this and show this up here. The way you calculate the standard deviation, the first thing you need to do is you need to calculate the variance. Okay. Step number 1 in calculating the variance, find the mean. Mean is 70, so we got that taken care of already. Now the second step for calculating the variance is to subtract the mean into each score. Now we have 45 scores here, which means it might be a little cumbersome, but there's a quicker way. So what you would do is you take, if you were doing it the traditional way, you take 50, which is the first score, minus 70, and you would get a negative 20, which would be the deviation. If you remember, we take that deviation, we square it up, and in this situation, negative 20 times negative 20 would give us a positive 400. Now, since 5 people scored 50, I could technically have to do this 5 times. But the thing is, if I were to do this 5 times, I would get 400 each time. So I'm just going to do it really quick and just show you. 50 minus 70 is going to give you negative 20. Square it up, you're going to get 400. 50 minus 70 gives you negative 20. Square it up, you're going to get 400. And 50 minus 70 gives you negative 20. Square it up, and you're going to get 400. Then you do it one more time. 50 minus 70 gives you negative 20. Square it up, and then you get 400 as well. So 400, 800, 1200, 1600, 2000. So it would end up, if you were to do this 5 times, you would get 2000. Now that's the long way. The other way that you could do that, since you know that you're going to get 400 every single time, I could do this 5 times, or I could multiply by 5, and I'm still going to get 2000. So that's what I'm going to do. Take 50 minus 70 gives me the deviation of negative 20. Square it up and get 400. I'm going to multiply this by 5, and I'm going to get 2000. Hopefully that makes sense to everybody, because I really don't want to do this 45 times, okay? So now that I have this, all I need to do is jump over to the next one. So I know that the next score is 60. And then again, 60 minus 70 gives me a deviation of negative 10. I square that up, and I'm going to get a positive 100, okay? Now I could do this 10 more times, because 10 people got 60. I don't want to do that. So what I would do here is I'll take this 10 and multiply it by its frequency, which is, I'd take this 100, multiply it by its frequency, which is 10, then I would get 1000. Now the next score, 70. 70 minus 70 gives you 0. I can stop at this point, because if you take 0 to square it up, you get 0. Multiply it by 15, you're going to get 0. So 70 minus 70 gives you 0, so we can just leave it like that. Jump over to 80. 80 minus 70 gives me the deviation of 10. We square this deviation up and we're going to get 100. Now, like I said, we could do it 10 more times, or I could just take this 100 and multiply it by 10 and I'm going to get 1,000. And then the last one, which is 90 minus 70 gives you 20. Square it up, we're going to get 400. We're going to multiply it by the frequency for 90, which is 5 again. We're going to get 2,000. Okay, now what we need to do at this point is we need to add all these scores up, because if you remember, the last part of the numerator of the variance equation is to sum it all up. 2,000 plus 1,000 gives us 3,000, plus 1,000 gives us 4,000, plus 2,000 gives us 6,000. So if we to add these square deviations up, we would get 6,000. Okay. Now that we have the top part of the equation, 6,000 for the variance. So if y'all remember the variance equation, it looks like the sum of the raw score minus the mean squared divided by n minus 1. So we've done all this. So we've done all this. So when this is all done, it's 6,000. We need to divide by n minus 1. We know our n is 45 minus 1 gives us 44, pretty simple. So 6,000 divided by 44 gives us a variance, which is equal to 136.36. But I'm not done, because we're not trying to find the variance. We're trying to find the standard deviation. How do we get the standard deviation from the variance? We take the square root, you hit the check mark button. So 136.36, the square root of it is 11.68, and that is our standard deviation. So now we can calculate z-scores, because we have both the mean, which is 70, and the standard deviation, which is 11.68. These are the two numbers we'll be using for the rest of this lecture. The mean of 70 and the standard deviation of 11.68. Okay, so again, when we know both the mean and the standard deviation, again, we can determine the percentage of cases that fall between the mean and any score and that fall beyond that score. So if you know the mean and you know the standard deviation, what you can determine is how much better, let's just say you were to take this, you took this class as well and you scored some score that's not that simple, that is not up there. Let's just say you got 85 and I gave you both the mean and I gave you the standard deviation. You could determine what percentage of the class you did better than. You could determine what percentage of the class did better than you. You could determine your percentile rank. You could determine what percentage of the class scored between your score and the mean, and so on and so forth. So that's what the standard, that's one of the things that the standard deviation provides us. Okay, now the way we're able to determine the percentage of cases that fall between the mean and our score and then beyond our score is by calculating what we refer to as a z-score. Okay, now what is a z-score? A z-score is the number of standard deviations that a raw score is either above or below the mean. Okay, so if your z-score is a positive number, you have a raw score which is above the mean. If your z-score is a negative number, you have a raw score which is below the mean. So if we were to draw out the normal distribution up here again, we know that the mean is 70, is the exact middle of the distribution. If you have a positive z-score, your raw score is above 70. If you have a negative z-score, your raw score is below 70, which is below the mean. Now, I'm going to show you how we get these numbers, but right now, one thing that's important to understand is that if you have the mean, if you know the mean and you know the standard deviation, you can determine the percentage of cases that fall between the mean and your score. One of the ways that we're able to do this is because we know that 68.26% of all the cases in the distribution, if you have a normal distribution, in this theoretical normal distribution, are going to fall within one standard deviation above and one standard deviation below. One standard deviation above and one standard deviation below. 68.26% of all the cases in a theoretical normal distribution are going to fall within one standard deviation above and one standard deviation below the mean, which means that 68.26% of all the cases in this theoretical final stats grades that we had are going to fall between 81.68 and 58.32. Okay. Now, according to that chart, we know that 95.46% of all the cases in the distribution are going to fall within two standard deviations above and two standard deviations below, which means that if you were to talk about what actual numbers, 95.46% of all the cases in the distribution are going to fall between 93.36 and 46.64. Okay, and then (99.72%) of all the scores in the distribution are going to fall within three standard deviations above and then three standard deviations below the mean. So 99.72% of all the cases in the distribution are going to fall within three standard deviations above. So three standard deviations above the mean is 105.04. Three standard deviations above the mean, and three standard deviations below the mean, so 34.96 on the low side. Now, I know what you're all thinking, where did you get these numbers from? Okay, now it's important to understand, let's not pay attention to these numbers right now. We'll get to that later. Where did we get these numbers down here? Now again, 68.26% of all the cases in the distribution are going to fall within one standard deviation above the mean and one standard deviation below the mean. One standard deviation is 11.68. One standard deviation is 11.68. The mean is 70. One standard deviation above the mean is 81.68. Because if you take one standard deviation, which is 11.68, you add it to the mean of 70. 70 plus 11.68 gives me 81.68. So 81.68 is one standard deviation above the mean. Now, the exact opposite, right? One standard deviation below the mean is 11.68 subtracted into 70. So 70 minus 11.68 gives me 58.32. So this is one standard deviation above, one standard deviation below. Now, so hopefully that makes sense to people how we got 81.68 and 58.32. Hopefully you all figured out by now that this 93.36, what is that? That is two standard deviations above. So this is 1 standard plus 1 standard deviation is plus 2 standard deviations plus 3 standard deviations is -1, -2, and -3 standard deviations. So if we have 2 standard deviations above the mean, well, what do you do with that 11.68? 70 plus 11.68 gives me 81.68, plus another 11.68 gives me 93.36. How do I know that this is the case? Because if I take 11.68 and I multiply by 2, I get 23.36. 23.36 added to 70 gives me 93.36. 23.36 subtracted into 70 gives me 46.64. And then the 3 standard deviations above is 3 standard deviations, or 11.68 plus 11.68 plus 11.68, or 11.68 times 3 gives me 35.04. 35.04 added to 70 gives me 105.04. 35.04 subtracted into 70 gives me 34.96. Okay, so that's how we got these numbers down here. Okay, that is, we just took the standard deviation, which we already know is 11.68. We either added it to the mean or we subtracted it into the mean, and that's how we got these 81.68, 58.32, and so on and so forth. How did we get these numbers up here? We will return to that later. But it's important to understand that, again, we know that 68.26% of all the cases in the distribution are going to fall within 1 standard deviation above, 1 standard deviation below. 95.46% of all the cases in the distribution are going to fall within 2 standard deviations above, 2 standard deviations below. And 99.72% of all the cases in the normal distribution are going to fall within 3 standard deviations above the mean and 3 standard deviations below the mean. All right, so how do we go about calculating z-scores? So the way we go about calculating z-scores is you need both the mean and standard deviation. We have both of those. So the mean is 70 and the standard deviation is 11.68. So what you do, the z-score formula, z is equal to whatever your raw score is minus the mean, which we know is 70, divided by 11.68. So like I said, if whatever score we have, if we know that score, we can calculate a z-score and we can determine the percentage of cases that fall between that score and the mean. Okay, we do that by calculating a z-score, and we go into the Appendix B, which is the standard normal table, which I'll expose you all to coming up. Okay. I might as well expose you to it right now. And we might as well have a score. So let's just say we have 85. Let's just say I scored 85 in that stats class. I'm the professor of the course, so must not be very good since I'm like not even getting an A in the class that I teach. But let's just say I got an 85. Okay. I go 85 minus 70. Okay, so I do 85 minus 70, and I got 15 at the top, right? So 15. We divide that by 11.68, and then that will give me a z-score, which is equal to, z is equal to 1.28. So my z value, we're going to round to 2 decimals in this situation. So our z value is equal to 1.28. Okay. Now that we have this 1.28, we can determine the percentage of cases that score between the mean, which is 70, and my score of 85. And we can determine the percentage of cases that did better than I did. So how many students scored better than I did? So what I do is I would come over to Appendix B. So Appendix B, I think is on page, it's at the back of the book. It's on page, for the 9th edition, the standard normal table is page 463, okay. But obviously I can't show the book right now, so I'm gonna put something else up here. I'm going to put PDF. So this is what you should be looking at when you look at the standard normal table, okay. So you're gonna see A, B, C, A, B, C, and it's gonna keep on repeating for a couple pages. A, B, C, A, B, C, A, B, C, and then A, B, C, okay. Now, what you're seeing when you look at an A column is the Z value. So that's the Z value, okay? And what you're gonna see when you look into the B column is the area between the mean and then Z. And then what you see when you look into the C column is the area beyond the Z, okay? So it's a lot of stuff. Let's just go ahead and like talk about our Z value of 1.28. So we have an A, which is the Z, the B, then we have the C, okay? Now again, we already know that the B is the area between the mean and Z. And then the C column is the area beyond the Z. Okay, so what we would do here in this situation, we're gonna go, our Z value is 1.28. If y'all remember, we just calculated it. And then we would go and we'd find this. Now, the other thing that I like to do here is, well, I don't like to do it. I just always do this. I always draw out the normal distribution because it helps me to understand, well, what's the B column? What's the C column? So I'm going to draw out the normal distribution here. Now we know that the mean is 70. Now the score that I got was 85. It's a positive Z value, so I know I'm to the right of the mean. So I'm going to draw where I think 85 would be. It doesn't have to be exact, but I think 85 would probably be around here. So I'm thinking some people did better than I did, but the vast majority of people did worse than I did. So I'm going to put 85 here, okay? Now, if I want to know how well I did in the class, how many students I beat, how many students I did better than, how many students did better than I did, well, if I want to know the percentage of students who score between my score, my raw score and the mean, I would look into the B column, okay? So this right here is the B column, is the area between the mean and then that Z value, or that raw score that corresponds to that Z value. And the C column is the area beyond that Z value, or the area beyond the score that corresponds to that Z value, okay? So now that we know that, and I have this drawn out, I can know what I need to look at. So I'm going to jump back to the table, the standard normal table that we were just looking at. So what I need to do in the A column, like I said, A, B, C repeats over and over again, I need to find the Z value of 1.28. Now, make sure that you find 1.28. Don't find 0.128 or 112.8 or something like that. You need to find 1.28. So I was looking here, looking here, looking here. Okay, I think I just found 1.28. I see 1.28. So in the A column, I see 1.28 right here. And then I see in the B column, 0.3997. And in the C column, I see 0.1003. Now, what does that tell me? What am I looking at here? Okay, what I am looking at is I am looking at proportions. Okay, if y'all remember from, I think, chapter 2, we were talking about proportions and we were talking about percentages. Now, the proportions always need to add up to 1.0, okay, for a distribution, okay? percentages always need to add up to 100%. And it's important to understand that when you're looking in the standard normal table, in the B column and the C column, you don't see percentages, you see proportions. If you want to convert these proportions to percentages, what you need to do at that point is multiply by 100, and then they'll become percentages. If you want to take a percentage and then you want to turn it into a proportion so you can look for that proportion in the standard normal table, you need to take that percentage and divide by 100 to get a proportion. Okay, so now that we have these numbers, 0.3997 and 0.1003, that tells me the proportion of students who did better than I did or beyond my score, and the proportion of students who did between my score and the mean. Okay, so I'm just going to write these numbers up here to help us understand them. So again, 0.3997, 0.3997 proportion of the course score between 70 and 85, and 0.1003 proportion did better than I did. Okay, now if you add these up, 0.3997 plus 0.1003, those do not add up to 1.0. Okay, so if you take 0.3997 plus 1.003, it is going to add up to 0.5000. The B column for any Z value, the B column plus the C column will always add up to a proportion of 0.5000. Okay. In percentage terms, you take 0.5000 multiplied by 100, and you're going to get 50%. Okay. Why is this important? It's important to understand that when you were looking in the standard normal table, you are only looking at 50% of the distribution. Okay. So here we are only seeing between the mean and a Z value, which is the B. And the C column tells you the area beyond that Z value, or beyond that raw score. It doesn't tell you the whole other side of the distribution. Okay? It assumes that you as a researcher knows that 50% of the distribution is on this side of the distribution, and 50% of the distribution is on the other side. Okay. Now, another thing that you may notice when you look into the standard normal table, I told you that the Z values could be either positive or negative, but you never see negatives in the standard normal table, and you don't need them. And the reason why you don't need them is because the numbers that you would see above the mean are the exact same numbers that you would see below the mean, because as we already discussed, the normal distribution is perfectly symmetrical. So there's no reason to have a negative 1.28, because the B column would still show 0.3997 if we did have a negative 1.28, and the C column would still show 0.1003 if we had a negative 1.28. So there's no point in like replicating that. So the numbers that you would see below the mean are the exact same numbers that you would see above the mean. So knowing that, just understand that when you're looking at the B and you're looking at the C, that it's only showing you 50% of the distribution, or 0.5000 proportion of the distribution. Okay. Now going back to the original kind of concept that we were talking about, well, what percentage of the class did I do better than? And what percentage of the class did better than me? Okay, well, there's two ways to figure this out. We can look into the B column, or we can look into the C column to figure this out. They tell me all the information that I need to know. Okay, so what I would do is I would take the proportion, I need to convert them to percentages. How do I convert the proportions to percentages? Again, we already discussed this. What you do is you multiply the proportions by 100. So if we take 0.3997 and then I multiply it by 100, so I'm going to get rid of these proportions. I'm going to convert these to percentages. 0.3997 in percentage terms is 39.97%. And then obviously 0.1003, you would have to also multiply by 100, and that's going to give you 10.03%. So there's two ways to figure out what percentage of the class did better than I did. I can look at the C column. If 10% of the class did better than approximately 10.03, but let's just round to 10% to make it simple. If 10% of the class did better than I did, well, what percentage of the class did worse than I did? 90%, right? So that's one way to figure out how well you did in relation to the rest of the class. The other thing that we could do is we could look into the B column. And then the B column tells me that I scored, or that about 40%, 39.97% up, so about 40% of the distribution score between my score and then the mean. So, but don't take that and think to yourself, okay, well, I did better than 40% of the class. No, you did better than 90% of the class. Because 40% between the mean and then your score. And then again, remember, the other 50% is on the other side of the distribution. So you'd have to add this 40% to this other 50% on this side. So you know, if you scored 85, I scored 85 on with my final score for that class, I did better than 90% of the class, and 10% of the class did better than I did. So that's essentially how you go about using the standard normal table. Quite a bit of stuff, I know, okay? But that's essentially how it works. Now, another thing is, some students probably were wondering to themselves, well, how did you get that 68.22, 68.26, the 95.46, and the 99.72%? So I'm going to show you just how to calculate the 68.26. So if y'all remember, we said that 68.26% of all the cases in the distribution are going to fall within one standard deviation above and one standard deviation below. So one standard deviation above 70 with our numbers is 11.68, right? So we would have 81.68 here, 58.33, 58.32 here. So what you would do is if you were to calculate a z-score for 81.68, we know that that's one standard deviation or one z-score above the mean, because one z-score is equal to one standard deviation. If you were to calculate a z-score for 81.68, it's going to be a pretty simple calculation. Z is equal to 81.68 subtracted by 70 divided by 11.68, which is the standard deviation, so mean standard deviation. 81.68 minus 70 is going to give you 11.68. 11.68 divided by 11.68 is going to give you a z value, which is equal to 1. Same thing with 58.32. 58.32 minus 70 is going to give you negative 11.68. Negative 11.68 divided by 11.68 is going to give you a z value, which is equal to negative 1. So same number. So our z value is 1. So let's just say we have a z value of 1. What would we do with this z value of 1? We would go to the table. So we would look in the A column for a z value which is equal to 1. So see, it's not here, it's not here, it's not quite this far. So we know that our z value of 1 is going to be somewhere around here. Okay, so we found the z value, which is, just realized I'm not sharing, so go ahead and share. So we go back to the standard normal table. So I need to find the z value, which is equal to 1.0. So we look for the z value, which is equal to 1.0. Come down, we find z value of 1.0. Now that I found that, this is the B column, and I see 0.3413. I'm going to draw that there. And in the C column, I'm going to see 0.1587. So right now, I'm really just going to focus on the B column. So if I know that 0.3413 proportion of the distribution fall between the mean and then one z value, I convert it to percentages, I know there's 34.13%, which means that 34.13% of the distribution score between 70 and 81.68. So we have here, we have 34.13%. And then also the z value of negative 1, it's the same 34.13%. 34.13% plus 34.13% gives us 68.26. That's how we went about finding that 68.26. And then you could do the same thing for the two z values, the two z-scores, and the three z-values for the three z-scores. So that's how we got that 68.26, that 95.46, and that 99.72% numbers, okay? Now back to this, which is the standard normal table. Well, you might think to yourself, where did these numbers come from? Did you all just make these up? Is this all hypothetical? Well, yeah, it's kind of theoretical. So the way they do that is there's a calculus formula that you're not going to learn in this class because it just takes too long to teach it. But there's a calculus formula in which you can determine the area under a curve, okay? So that's why if you're saying to yourself, well, why does it say the area between the mean and the z-value and the area beyond the z-value, even though, like I said, we're talking about percentages here? It's because it's a calculus formula that's looking at the area under a curve. Now, but it also applies to percentages and just normal distributions that we would see out there in the real world. Okay, so that's how we get these numbers. Yes, they're theoretical, they're hypothetical. You're not going to learn that formula if you take this class, but I mean, I know how you're all dying to take more advanced stats classes, and as you take more advanced stats classes at the university, you're going to learn how to actually go about calculating that. So you will have plenty of fun with that in your next upper division stats class. But for now, let's just accept that these numbers are theoretical. They are hypothetical, but they closely mimic the real world, okay? So now that we learned how to, let's go ahead and jump back to PowerPoint. So now that we know how to use a standard normal table, again, the B column is the area or the percentage of scores between the mean and a z-value or a raw score. The C column is the area beyond a given score. So the C column is the area beyond a given score. If you know the z-value, which you need both the mean and standard deviation to calculate the z-value, you can determine the percentage of cases that fall between your score and the mean and the percentage of cases that fall beyond. So you can determine just how well you did in relation to the rest of the class based upon those two pieces of information when you have a normal distribution. All right, so that's how you go about finding the area between the mean and then your z-value. Right now, we're going to talk about how to take any z-score and then transform it into a raw score. Now, why would you want to do this? So the reason why you might want to do this is if you, let's just say that you're in a situation where you're applying to certain, well, let's just say you apply to an Ivy League school. And what a lot of people don't know is that, you know, in some programs, like graduate level programs, I think sometimes even like nursing programs, things like that, is everybody can't get A's, okay? No matter how good everybody is, everybody doesn't get A's. Like, for example, if you're at an Ivy League school, I think like Harvard University, they really only give A's to the top 10% of the distribution. So in order to get an A, you really are one of the top 10 students, okay? So if everybody's scoring like 90, 95, 99, 100, you know, 92, 93, you get that 90, you're kind of like at the bottom of the class, right? So what they do is in schools like that is they take the top 10% of the distribution, and they only give 10%, the top 10% of the distribution an A. Okay. Now let's just say that you're in a school like that, and you need to, you know that you need to be in the top, you know, whatever percent of the distribution in order to get an A in the class. Okay. Well, what are you going to do? Well, what's the process going to be like? So what you would want to do If you know the mean and you know the standard deviation, so you know just historically how people have been scoring on these exams, just say the SAT or the GREs or the MCATs, you need to be in the top 5% of the distribution in order to get into the medical school you want to. Let's just say, use that as an example, the MCAT test. And then you know historically how people have scored on the MCAT. If you know the mean and you know the standard deviation for how people have historically scored on the MCAT, you could find the raw score that you need to get in order to be in the top 5% of the distribution, okay? Now, how would you do that? Let's just say that we're trying to get into the top 5% of the distribution. What raw score do we need? And we're still going to use our same numbers, which is the mean of 70, standard deviation of 11.68, and all that stuff, okay? So our mean is still 70. Standard deviation is 11.68. What raw score would we need to be in the top 5% of distribution? Usually I would just keep top 10%, but we already figured out the top 10%. You need a raw score of 85 to be in the top 10%. Okay. So what you would do here is, the first thing you want to do is you want to start off by drawing out the normal distribution. Okay. So you're going to draw the normal distribution out. We know the mean is 70, and we want to know what raw score we need to get. So what raw score we need to get to be in the top 5% of the distribution, where only 5% of the class did better than we did. So we need to find the score we need to get to be in the top 5% of the distribution. So we would know that we would be looking into the C column because we'd be looking for this top 5%. Now, again, when we're looking at percentages, we're not going to see percentages standard normal table. What are we going to see? Proportions. So we need to take this 5%. This is going to be 40. The B column is going to be 45%. The reason why I know that is because, like I said already, the B column plus the C column always adds up to 50% of the distribution, or a proportion of 0.500. That's how I know that we're going to have 45% of the B column. Okay, so what I need to do is I need to take these two numbers, I need to convert them to proportions. Okay, now how do I do that? To take a percentage, convert it to a proportion, you divide by 100. So 5 divided by 100, I can already tell you what the answer is. I already know what the answer is. It is 0.0500. So 0.0500. And then here you'd have 0.4500 if you divide this by 100. So those are the two numbers we're going to be looking for. We're going to be looking for 0.0500 in the C column and 0.4500 in the B column. Now that will give us the Z-score that we need to use to find our raw score that we need. So once we have that Z value, we then plug that into this equation, which is a raw score equation. So the raw score is equal to the mean plus the Z times the standard deviation. We know what the mean is and we know what the standard deviation is. What we don't have is the Z value. And this is how you're going to go about getting that Z value. Okay, so now that we have this, we have 0.05000. I'm going to find the standard normal table. Okay, so we go ahead and jump this, find this. Okay, so we need to find in the C column 0.05000. Now that you might be thinking to yourself, well, here it is right here. Nope, that's 0.5000. We're looking for 0.0500. Okay, so we need to find that in the C column, or we could find 0.4500 in the B column, whichever one we find faster. So as we're progressing, don't see it. Okay, now I finally found it. So this is not the exact number, but this is the closest number that we're going to find, 0.0495. Okay, so 0.0495 is the closest number we're going to find to 0.0500, and then 0.4500 is the closest number we're going to, 0.4505 is going to be the closest number we're going to find at 0.4500. So again, I'm not going to find this. I'm not going to find this exact number. I'm going to find, instead of this exact number, I'm going to find 0.0505. So you need to find the closest number. And then here, we're going to find, actually 0.0495, I believe it was. 0.04495, and then here we had 0.4505, and then this B and then this C correspond to a Z value which was equal to 1.65. Okay, I'll jump back to that so y'all can see that. 1.65, this is the closest number to 0.4500, this is the closest number to 0.0495. Like I said, when you look through this table, a lot of times you're not going to find the exact number that you're looking for. So what do you need to do at that point? Find the closest number that you can find. Now that we have these numbers, we have this 1.65, which is the Z value. Now we're just going to plug it into that raw score formula that we had up there. And that raw score formula, if you all remember, is Y, which is the raw score, is equal to the mean of Y plus the Z times the standard deviation. Now we have all three components here. We have the mean, which is 70, the Z, which is 1.65, and then the standard deviation, which is 11.68. Here you want to follow the order of operations, 1.65 times 11.68. What is that going to give us? That is going to give us 19.27. We take 19.27, we add it to 70, so we do multiplication first, then we do addition, and our raw score that we need to be in the top 5% of the distribution is 89.27. As long as I get 89.27 or above, I'm going to be in the top 5% of the distribution. Then I get my A, or I get, into whatever medical school program that I might be trying to get into. So that's how you take any Z value and then you convert it to a raw score to find the raw score to be in a certain percentile rate that you might want to be. So that's one of the applications that you might see for that. Okay. One thing that I always do is I always draw out the normal distribution because it helps me, one, to conceptualize what it is that I'm looking for. When you read the homework questions, it's probably a little bit complex if you don't draw it out. So I would seriously suggest you draw it out. That's the one thing. And then two, it'll help you understand, like, okay, well, do I look into the B column? Do I look into the C column? Do I look below the mean? Do I have a negative Z value? Do I go above the mean? Do I have a positive Z value? And, using that helps. All right. So now what we're going to do is we're going to find the area between, let's just go ahead and give this a shot. Let's find the area between the mean and a positive Z score. So how would you go about doing this? Well, we already talked about 85, right? We know that 85 minus 70 gives you 15 divided by 11.68, you're going to get 1.28. Okay. You take these numbers, you look it up in Appendix B, and what you would find in the B column, which is the area between the mean and that Z value, would be 0.3997. So you know that 40% of the distribution score between 70 and 85. We actually already did that. Let's go ahead and do it for a negative Z value. How would you do this? So what you would do here to find the percentage of students who score between 65 and 70, you draw it out, and then you calculate a Z score out of 65. So Z for the 65 minus 70. Okay, you're gonna get negative 5. Okay, you take that negative 5, you divide it by 11.68, and you're gonna get negative 0.43. Okay, so that's the Z value. You take that 0.43, you look it up into, look for it in the B, Appendix B. So you would come over here, you look for that 0.43. You're not gonna see negative numbers as we discussed already. We're gonna look for 0.43, and what are we gonna see in the B column? So this is the 0.43. What are we gonna see in the B column? 0.1664, which we already know is equivalent to about 16.64%. So we know that's about 17% of the distribution score between 65 and 70. Let's go and find the area between two z-scores on the same side of the mean. Now what you need to do, you need to find two z-values. One for 74 and one for 84. So what you would do is you'd find the z-value for 74. 74 minus 70 gives you 4. You take 4 and you divide it by 11.68. 4 divided by 11.68. And then your z-value in that situation is going to be 0.34. So for 74, the z-value is going to be 0.34. And then for 84, you're going to get 14 divided by 11.68. And you're going to get a z-value which is equal to 1.19. So you go look for 0.34 and 1.9. Let's go with 1.20. For rounding properly, it's 1.20. So now you go find those 0.34 or 1.20 in the table. So when we see 0.34, we're going to see the percentage of people who score between 70 and 74 is 13%. And then when you look for 1.20, 1.20, we see 1.20 here. The percentage of respondents score between 70 and 84 is 38. So if we just wanted to know the percentage of people who score between 74 and 84, what we need to do is subtract this 13%, and we would have 25%. Okay, 25% of the distribution score between 74 and 84. So that's also the way it would look. All right, so let's find the area between two z-scores on opposite sides of the mean. So what you do for, let's just say you're trying to find it for 62 and 72. Calculate a z-score for 72. 72 minus 70 gives you 2, divided by 11.68. We'll give you a z-value of 0.17. Do it for 62. 62 minus 70 divided by 11.68 is going to give you negative 0.68. Okay. So now that you have these two numbers, what you do is you take these two z-values and you go to that table. Okay. So if you're looking for 0.17, you're going to find 0.0675. So again, 0.17 as a z-value. You see 0.0675 in the B column. And then the other z-value, which was 0.68, negative 0.68, you're going to find negative 0.68. See 0.2517. Okay. Now, when you have that, you take those two numbers, 0.0675, 0.2517. I would suggest that you draw it out so you can see that 70 to 72 is on the right side, 70 to 62 is on the left side. So what you do, since you're trying to find the area between 62 and 72, you're going to add these two together. That's why I say it's important to actually draw these things out. Okay, so let's go ahead and find an area above a positive z-score and below a negative z-score. So what you do for 85, we already calculated 85, so we know 85 minus 70 gives us 15, divided by 11.68 gives us 1.28. Which is, if you look into the C column, you're going to see 0.1003, which is equal to 10.03%. Now, let's just say that you're doing it for 50. You're going to look into the C column for 50 as well, because you want to know below 50. So the area beyond 50. So what you're going to do is you take 50 minus 70, it's going to give you negative 20. You're going to divide it by 11.68. And you're going to get negative 1.71, which obviously the negative denotes that it's below the mean. And then the percentage that you're going to see there, well, you're going to see a proportion of 0.0436. So if we go over there, we find 1.71. You're going to see a proportion of 0.0436, which if you multiply by 100, is going to give you 4.36%. So what you do is, since we're seeing the area below 50, we're looking to the C column. The area above 85, we're again looking into the C column, because we don't really look into the B column, we're looking between the area between the mean and the z-score, between the mean and the z-score. We're looking at the area beyond, we're looking into the C column. Okay, so what we also want to do is we want to, let's just say we're trying to find the raw score that bounds the top 10% of the distribution. Okay, so we know 10% is equal to a proportion of 0.100. Okay, so what you would want to do in that situation is you would want to take the proportion of 0.100, and then you would look for that in the C column. Okay, because obviously what we do in this situation, I think it might be a little bit more helpful if I draw it out again. What we do in this situation the normal distribution. We do this for the 5%, but let's go ahead and do it for 10%. You look for what is equal to 10% in the C column. And we know obviously 10 divided by 100 is going to give us a proportion which is equal to 0.100. Okay, so we're going to look for 0.100 in the C column. Now, I'm also going to be looking for 0.400 in the B column, because I know that this is 40%, this is 10%, always equals 50%. Now, when I look for 0.1000 in the C column, I'm not going to find that number. Again, you're rarely going to find the exact number that you're looking for. So what I do is I'm going to come over, and I can see that 0.1003 is the closest number to 0.100. Okay, so we found the closest number. 0.3997 is the closest number to 0.4000, and then the z value that corresponds to that is 1.28. So we use that z value of 1.28, and we plug it into this equation, which is the mean, which is 70, plus 1.28, which is the z value times the standard deviation of 11.68. 1.28 times 11.68 gives us 14.95. We take this 14.95, add it to 70, and we're going to get a raw score of 84.95. So what raw score do you need to get to be in the top 10% of the distribution? You need a raw score which is equal to 84.95 to be in the top 10% of the distribution. Okay, so let's go ahead and find the percentile rank of a score higher than the mean. So suppose your raw score was 85. Let's calculate the percentile to see where in the class you rank. So what percentage of the class you did better than, what percentage of the class did better than you did. Z-score, we already know, because we've done 85 like 5 times already. So I think I need to change these slides up a little bit. The Z value is going to be 1.28, okay? Now that we have that Z value of 1.28, what we're going to do is we're going to look into column C, which we know is 10%. It's also up here. And then you're going to take that 10%, or the proportion of 0.1003, pretty much the same thing. If you can conceptualize 10% in proportion terms is equal to 0.1003. Subtract it to 1.00, which is the total distribution, and you're going to be left with 89.97, which is the percentage of the class you did better than. So what you do is you'd have 10% of above your score, then obviously the other 90% would be below your score. The other thing that you could do, which I believe we did a little bit earlier, is you could take, with the B column, you have the percentage of students who score between your score and the mean is about 40%. You take that 40% here, add it to the 50% on the other side, and you have 90% of the distribution. All right, so let's find the percentile rank of a score lower than the mean. So let's just say you have a raw score of 65. This is another number that we already calculated. So we already know that the z value, 65 minus 7, negative 5, divided by 11.68 gives us negative 0.42 approximately. So we take that z value, and then we're going to look into the C column. And the C column is going to give us 0.372, which is approximately 33, 34% of the class did worse than we did if we scored 65. So again, the reason why we're going to look into the C column is because we want to know what percentage of the class did worse than we did, so that we know our percentile rank. Okay. We already found how to find the raw score you need to get to be in the top 5% of the distribution. So to be in the 95th percentile. That raw score was, of course, 89.27. So I don't see any point in redoing that here. So like I said, I think the best way to approach this and to understand this stuff, which is actually pretty complex, is to draw it out. If you don't draw it out and you're doing the homework, you are making your life substantially harder. Because if you just draw it out, you know, you can see, okay, well, am I looking to the B column? Am I looking into the C column? Am I above the mean? Am I below the mean? You know, what is it asking? You know, and so if you draw it out, it makes it a lot easier to actually consider B versus C, left, which is left side of the mean, which is below the mean, which is a negative z value, right side of the mean, above the mean, which is a positive z value, and it can help you to conceptualize which column you're going to be looking at. Anyways, other than that, you know, that's pretty much. I have 2 vicious attack dogs, and then they're making noise right now. So anyways, so like I said before, draw it out. It's going to help you out substantially. And but yeah, so there's 2 equations that you're going to want to need to use: the z-score formula and the raw score formula. That's another thing that you want to pay attention to. You want to make sure that you're using the right formula, because if you're not using the right formula, you'll never be able to answer the question. So the raw score formula is when you're trying to find a raw score from a percentage or from a z value. And the z-score formula is the formula that you want to use if you're trying to find a percentage from a raw score. So if you have the raw score already, don't use the raw score formula. No point in that. And if you have the percentage already, no point in using the z value. You're going to want to use the raw score formula, right? All right, we'll get back to this on chapter 6. This one's a doozy, but hopefully you all can kind of if I went too fast, pause it, rewind, rewatch the video a couple times, and it should help you out quite a bit, right?